All right, yeah, I'm Thomas Jones. I'm going to be talking about enhanced rock weathering in unfavourable landscapes. So we've seen all of these reactions talking about enhanced rock weathering and mineral carbonation in general. The most important ingredient in this whole reaction is water. It brings CO2 into contact with soil, it facilitates the reaction, it carries cations to and from reaction sites, and it transports carbon wherever it's going. So what happens if we don't have water for this reaction? And it's a pretty important thing to think about because a lot of Australia and a lot of the global agricultural landscape doesn't have free water all the time. If we have a look at the green on this map, that's our farming area. And if wherever it's matched up with the black, which is our mafic rock, is where our ERW CDR capacity lays. But when we have a look at the land use of this area, there's 850,000 square kilometres that in some way or another are classified as dry land, which means that in Australia, there's a lot of land that's going to be targeted for ERW that doesn't have this water. So we've been doing some characterization studies about different rock flowers in Australia, and kind of alongside it, we ran this experiment to see how these rock flowers interact with CO2 without the presence of water. So for this experiment, we took 6 commercial mineral amendments off the shelf. We had 12 quarry materials, and we compared them to wollastonite and olivine as our mineral references. And we submerged them in 100% CO2 for 2 weeks to see what happens. When thinking about characterization of these rock flowers, I mean, we've heard today and you've heard over the last couple of years, we use basalt to drive this process. And basalt is basalt. But when you break it down, using XRD in this case, into reactive and less reactive weathering phases, we see that we get a huge variation in what's actually weathering in these basalts. So our commercial samples, quarry samples, we get a range of about 20 weight percent to 90 in both. And really, if you look at the ICP, all of these have roughly the same amount of calcium, iron, magnesium. But the amount of calcium, magnesium that you're actually going to receive on an anthropogenic timeline is very different. And of course, our wollastonite and olivine are very high. So we know that in ERW, we need water to drive this reaction. So really, nothing should happen with these samples when you submerge it in CO2 dry. And if something were to happen, it would pretty closely mimic our reactive calcium, magnesium, iron phases. So when we weighed this material after 2 weeks, we saw big increases in weight percent. We used FTIR to confirm that more or less all of this weight increase is new secondary carbonate that is formed, which is really bizarre. It was really bizarre to me to see this. Another thing straight off the bat is that the quarry material, straight from the quarry, on average performed better than the commercial mineral amendments. But this data just gets weirder and weirder. It's not correlated with pH or moisture content within these samples. And when we plot it up against the reactive phases for the commercial products, yes, there's a pretty nice correlation between the increasing amount of reactive phases and how much secondary carbonate was produced. But for the quarry material, there was no correlation at all. So even though it was increasing at a higher rate on average than the commercial products, we don't know why. And this is what rattles around in my head all the time. Chemistry and thermodynamics predict potential CDR, but realizable CDR is governed by something else. In less than ideal conditions, this something else is going to become more and more important. And especially because most of the world's ERW is going to be occurring in less than ideal conditions. This something else is going to be site-specific. It's going to change region to region. But one something else that is going to be happening wherever this process is occurring is the microbial community that drives this process. Microbes are really good at CDR. They've been doing it for 3.5 billion years. It's a nice stromatolite. And they also drive geochemical cycling in soils. So, of course, naturally, they're going to have an impact in some way on ERW. And what does this mean? Microbes in the soil are really good at breaking down primary mineralogy, but at the same time building up secondary precipitates, walking the fine line between weathering and precipitation. Both of these images were taken in the same sample, a millimetre apart. And we can see primary mineralogy turning to mush, and at the same time, secondary carbonate precipitates being precipitated. So we've been exploring this as well, doing some experiments using soil-derived and quarry-derived microbial consortia and inoculating them into alkaline and acidic ERW experiments. And we're seeing some really interesting things. This one in particular, if you look up in the top left, up here in that kind of ghosty white thing up there. So we've got these two in particular, silicate grains that are encrusted with something. And what we've actually got is a silicate mineral, a weathering silicate boundary, and the secondary carbonate cement. And that carbonate cement is full of fossils. So if it's not biogenic, it's bio something. It's allowed for by biology. So this is happening on the surface, but we also see it throughout the soil columns, where we have primary calcium minerals a little bit underneath. We have the same minerals weathering, and then a little bit further down, we get these new calcium cements that are precipitating. So those top green minerals are silicates. That cement is a carbonate and it's full of fossils. So this is a biogenic process. Thermodynamics sets the potential, but something else sets the rate. And it's really important to think there's no such thing as abiotic at Earth's surface. Every single process that's happening uses biology in some way. And it's going to be impacting your ERW projects. So it's something we have to consider. Thank you.